Virtual memory is like a huge bookshelf that does not really exist in your room, but you act as if it does. Address space abstraction. Each program thinks it owns a private set of numbered boxes, addresses. The computer hides the fact that these boxes are actually stored in many different places, just like a library uses a catalog to point you to the right shelf. Protection. The catalog, the operating system, checks that a program only opens its own boxes, preventing one kid from reading another kid's diary. Cost benefit. Building a real bookshelf for every program would be extremely expensive. Memory is limited. Virtual memory lets many programs share the same physical shelves, using only the space they really need, and swaps unused pages to a slower storage, like putting some books in a warehouse. The benefit outweighs the extra work of looking up where each box really lives, just as it is easier to keep a single catalog than to buy a new bookshelf for every story you read. A page table is the catalog that maps virtual boxes to real shelves. There are 3 common ways to organize the catalog. Single-level page table, a giant array where each entry tells where one virtual page lives. It is simple, like a phone book where the line number equals the page number. The downside is that the whole book must be kept in memory, which can waste a lot of space. Hierarchical multi-level page table, the catalog is split into several smaller books. The first book tells you which second-level book to look at, and that second book finally gives the physical address. This is like a library where the top-level index points to a section index, which then points to the exact shelf. It saves memory because unused sections need not be created. Inverted page table. Instead of one entry per virtual page, there is one entry per physical frame. The entry stores which virtual page and which process is currently using that frame. This is like a reverse lookup. You ask who is sitting in this chair. It greatly reduces memory for systems with many processes, but lookup can be slower because you may need to search. Each design trades simplicity, memory overhead, and lookup speed, just like choosing between a single big map, a set of regional maps, or a reverse directory of where cars are parked. When a program asks for data at a virtual address, the computer splits the address into 2 parts. Page number. Virtual page number tells which page in the virtual address space we are looking at. Offset tells the exact byte inside that page. The page number is looked up in the page table, or TLB, to get the physical frame number, PFN. The final physical address is physical address equals PFN left shift page offset bits bitwise or offset. Example 32-bit system, 4 kilobyte pages. Page size equals 2 to the 12 equals 4096 bytes. Offset equals 12 bits. Virtual address equals 0x1234 ABCD, which in binary is 0001 space 0010 space 0011 space 0100 space 1010 space 1011 space 1100 space 1101. VPN equals upper 20 bits equals 0x1234. Offset equals lower 12 bits equals 0xBCD. Suppose the page table gives PFN equals 0x5F3. Physical address equals 0x5F3 left shift 12 bits bitwise, or 0xBCD equals 0x5F30000 plus 0xBCD equals 0x5F3BCD. Example 64-bit system, 2 megabyte pages. Page size equals 2 to the 21 equals 2,097,152 bytes. Offset equals 21 bits. Virtual address equals 0x0000 underscore 7 FFFF underscore FFFF underscore F123. VPN equals upper bits. 64 minus 21 equals 43 bits. Offset equals lower 21 bits equals 0x123. If PFN equals 0x1 a 2b3c4, physical address equals 0x1 a 2b3c4 left shift 21 bits bitwise, or 0x123. The same idea works for any page size. The offset size changes, but the split and combine steps stay the same. Explanation: multi-level page tables break a huge table into smaller pieces, reducing memory that must be kept in RAM. 2-level example. Assume 32-bit virtual address, page size equals 4 kilobytes, 12-bit offset. Remaining bits equals 20, split into 2 10-bit indices, level 1 index and level 2 index. Each level 1 entry points to a second-level page. A 4 kilobyte block that can hold 2 to the 10 equals 1024 entries. Memory needed. Level 1 table size equals 2 to the 10 entries times 4 bytes equals 4 kilobytes. Each populated level 2 table also costs 4 kilobytes. If a process uses only 100 kilobytes of virtual memory, it needs about 100 kilobytes divided by 4 kilobytes equals 25 pages, becomes 25 level 2 tables plus 1 level 1 table, equals 26 times 4 kilobytes, approximately 104 kilobytes, far less than a single 4 gigabyte flat table. 3-level example, 64-bit 4 kilobyte pages. Virtual address bits equals 48 typical canonical address. Offset equals 12 bits. Remaining equals 36 bits, becomes split into 3 12-bit indices. Each table level holds 2 to the 12 equals 4096 entries, each entry 8 bytes, 64-bit PFN. Size of one table equals 4096 times 8 bytes, equals 32 kilobytes. If a process maps 1 gigabyte of memory, number of pages equals 1 gigabyte divided by 4 kilobytes, equals 2 to the 18 pages. This occupies 2 to the 6 equals 64 leaf entries per level 2 table. So you need 2 to the 6 level 2 tables and 2 to the 0 level 1 tables. Becomes total memory approximately 1 plus 64 times 32 kilobytes, approximately 2.1 megabytes. Again, far smaller than a flat table of 2 to the 36 entries. General formulas. For an n-level table with each index using I bits and entry size e bytes. Size of one table equals 2 to the I times e. Total overhead approximately equals number of populated tables times 2 to the I times e. These calculations show why modern OSes favor multi-level designs. They keep only the tables that are actually needed, saving a huge amount of RAM. Why it matters. Think of a city's address system. Instead of writing every house's full address on a single massive sheet, you first write the street name, then the block number, then the house number. Only the streets you actually have houses on need a block list, which saves paper and time. The translation look-aside buffer, TLB, is a tiny, very fast cache that stores the most recent virtual to physical translations. Associativity, the TLB works like a small set of lockers. In a fully associative TLB, any entry can go into any slot, like having open seating. In a set associative TLB, the lockers are grouped. Each virtual page number, VPN, maps to a specific set, then any slot in that set can be used. This reduces hardware complexity while keeping lookup fast. Entry format, each TLB entry typically holds VPN or part of it, PFN, the physical frame number, protection bits, read write execute flags, a valid bit. Optionally a global bit used by the operating system for kernel pages. Hit lookup flow. Step 1, the CPU generates a virtual address. Step 2, the hardware extracts the VPN and queries the TLB. Step 3, if an entry matches a hit, the PFN is read combined with the offset and the physical address is produced in 1 clock cycle. Step 4, if no entry matches a miss, a page table walk is started, the result is placed in the TLB, replacing an old entry and the instruction resumes. Analogy, imagine a school desk drawer where you keep the most used pens. When you need a pen, address translation, you first look in the drawer, TLB if it is there, you grab it instantly hit. If not, you must go to the supply closet page table, which takes longer. Key point, because the TLB is on the order of 32 to 256 entries, it can hold translations for only a few megabytes of memory, yet that covers the working set of most programs, dramatically speeding up memory accesses. Explanation: to understand TLB performance, we use the average memory access time, a MAT, formula, similar to CPU cache analysis. An MAT equals T hit plus open parenthesis, miss rate times miss penalty close parenthesis. T hit dash time for a translation when the entry is in the TLB, often 1 to 2 nanoseconds. Miss rate dash fraction of accesses that miss the TLB, open parenthesis 1 minus hit rate close parenthesis. Miss penalty dash extra time to walk the page table, typically 10 to 100 nanoseconds, depending on levels and whether the walk hits in L1/L2 caches. Numeric case study. T hit equals 1 nanosecond. TLB hit rate equals 98%, goes to miss rate equals 0.02. Page table walk cost equals 30 nanoseconds, 3-level walk, each level hit in L2 cache. A MAT equals 1 nanosecond plus 0.02 times 30 nanoseconds equals 1 nanosecond plus 0.6 nanoseconds equals 1.6 nanoseconds. If the hit rate falls to 90%, miss rate equals 0.10. A MAT equals 1 nanosecond plus 0.10 times 30 nanoseconds equals 4 nanoseconds. The slowdown is more than 2 times, showing why a high TLB hit rate is crucial. Hit rate formula can be estimated using the working set size W and TLB coverage C. Hit rate approximately min of 1, C divided by W, where C equals open parenthesis number of TLB entries times page size close parenthesis. If a program uses 8 megabytes of active memory and the TLB can hold 64 entries of 4 kilobytes pages, C equals 64 times 4 kilobytes equals 256 kilobytes. So hit rate approximately 256 kilobytes divided by 8 megabytes equals 0.032, 3.2%. In real systems, larger page sizes, for example 2 megabytes huge pages, increase C dramatically, raising the hit rate. Thus, a MAT highlights the trade-off. More TLB entries or larger page sizes reduce miss rate, lowering overall access latency. When the TLB is full and a new translation must be inserted, the hardware must decide which old entry to evict. Common policies: LRU, parentheses least recently used close parentheses dash the entry that has not been used for the longest time is thrown away. It approximates optimal behavior but needs extra bookkeeping, for example counters or stack. Example simulation: for a sequence of VPN accesses, open bracket 1, 2, 3, 1, 4, 5, 1, 2 close bracket with a 3-entry TLB. LRU yields 2 hits, the second one and the final 2. FIFO, parentheses first in first out close parentheses dash the oldest entry, the one inserted first, is replaced, regardless of how often it was used. Using the same sequence, FIFO would evict entry 1 after the third insertion, resulting in more misses. Random dash an entry is chosen at random. It is simple to implement and can avoid pathological worst-case patterns, but on average it gives a lower hit rate than LRU. Impact on hit ratio dash empirical studies show LRU often yields a 5 to 10% higher hit rate than FIFO for typical program traces. Random may be within 2 to 3% of FIFO, but with negligible hardware cost. Simple simulation code: sudo python : sec equals open bracket 1, 2, 3, 1, 4, 5, 1, 2 close bracket. TLB equals open bracket close bracket. Capacity equals 3, hits equals 0, for V in sec : if V in TLB : hits plus equals 1 hash LRU move to front, TLB remove V TLB insert 0 V else : if length of TLB equals capacity : TLB pop, hash evict LRU last element. TLB insert 0 V print open parenthesis, LRU hit rate, hits / length of sec close parenthesis. Explanation: a page fault occurs when a program accesses a virtual page that is not currently resident in physical memory. The operating system must then bring the page from secondary storage disk into RAM. Fault service time, abbreviated FST, equals time to handle the fault equals disk transfer time plus OS overhead plus possible page replacement time. Disk seek approximately 5 milliseconds, rotational latency approximately 4 milliseconds, transfer approximately 0.5 milliseconds, total about 9.5 milliseconds. Adding OS work approximately 0.5 milliseconds, therefore FST approximately 10 milliseconds. Effective access time, abbreviated EAT with faults. EAT equals 1 minus PF times memory access time plus PF times FST, where PF equals page fault rates. Thrashing analysis. Thrashing happens when the fault rate becomes so high that the CPU spends most of its time handling faults rather than doing useful work. Let P equals number of pages a process needs for its working set. M equals number of frames allocated to the process. If P greater than M, the system will constantly replace pages, leading to high PF. A simple threshold model. PF is approximately the maximum of 0 and P minus M divided by P. When PF greater than 0.1, that is more than 10% of accesses cause faults, the system is considered to be thrashing. Example, process needs 200 pages. Operating system gives it 150 frames. PF is approximately 200 minus 150 divided by 200 equals 0.25, which is 25% fault rate. EAT is approximately 0.75 times 100 nanoseconds plus 0.25 times 10 milliseconds equals 2.5 milliseconds dominates. The CPU would be idle most of the time. Solutions include reducing the working set size, changing program behavior, increasing allocated frames, more RAM, using larger page sizes to bring more useful data per fault, employing working set or page fault frequency algorithms that adjust allocations dynamically. Page size, the amount of memory covered by one virtual to physical mapping, influences three key aspects. Fragmentation, if a program needs 6 kilobytes and the page size is 4 kilobytes, it will occupy 2 pages, wasting 2 kilobytes. Internal fragmentation. Smaller pages reduce waste but increase the number of pages, raising page table size. TLB coverage equals number of TLB entries times page size. With 64 entries and 4 kilobyte pages, coverage is 256 kilobytes. With 2 megabyte huge pages, coverage is 64 times 2 megabytes, which is 128 megabytes, dramatically increasing the chance that a needed address is already in the TLB. System throughput, larger pages mean fewer page table entries and fewer TLB misses, improving throughput. But they also increase I/O time per page fault because more data must be read from disk. Trade-off calculation example. Assume a workload with an average working set of 32 megabytes. 4 kilobyte pages. Number of pages equals 32 megabytes divided by 4 kilobytes, which is 8,192 pages. Page table entries are 8,192. If each entry is 8 bytes, the table size is 64 kilobytes. TLB miss rate with a 64 entry TLB is approximately 64 divided by 8,192, about 0.78%, negligible. 2 megabyte pages. Number of pages equals 32 megabytes divided by 2 megabytes, which is 16 pages. Page table size is 16 times 8 bytes, 128 bytes, tiny. TLB miss rate is 64 divided by 16, greater than 1, meaning all pages fit, so miss rate is 0. However, a page fault now transfers 2 megabytes from disk instead of 4 kilobytes, increasing fault service time by a factor of 512. If the fault rate is low, for example 0.1%, the larger page size yields higher overall throughput because the saved TLB misses outweigh the occasional larger I/O if the fault rate is higher. The cost of moving 2 megabytes per fault can dominate, making smaller pages preferable. Guideline: use the smallest page size that still gives acceptable TLB coverage for the typical working set. Modern operating systems often support both regular 4 kilobyte pages and huge pages of 2 megabytes or 1 gigabyte, and let applications choose based on their memory access pattern.